the exam will only on magnets. Okay, so this is the next topic. It's about waves, and today I'm planning to go over introducing waves and talk a little bit about electromagnetic waves if we have time, unless we will take the remaining piece to the next class, and then we'll talk about light. Light is another type of wave, so we'll talk about light as well following with this topic. All right, so when we talk about waves, now if there are a vibration, like it's up and down vibration, it's a periodical wiggle, so we call this as a vibration, or it's like something disturbing, right? So if I tap on the table, it's a vibration, so I'm vibrating the materials in here. And if I tap on the water, I can vibrate the water, right? So anyway, vibration is a periodical wiggle in time. So here, like in this diagram, it's not really a diagram, right? So it's a scratch mark here. But I mentioned, I just wanted to demonstrate like it's something going up and down, up and down. It's not moving in the space, but within the time it vibrates, right? You can even think about a simple model like a pendulum, you know, like grandpa clock. There's a ticking bob, right? It ticks. So that's a pendulum. So that's vibrates, right? So they are vibrating. Then when we go to the wiggle that's happened both in space and time, that is a wave. So here, like in the second diagram over here, so it vibrates at the same time it travels in the space with the time, right? So that is a wave. All right, so there are a lot of examples of waves. So sound waves, right? So when I speak, it's the air molecules get vibrates and it's propagate the energy, and then you will hear it. So that propagation of a wave through the air will come to our ear, and the eardrum will vibrate, and our brain is translating that wave into a sound that we can understand, right? So sound is a wave. And radio waves. So if you ever listen to a radio, I think most probably when you're driving, you're listening to the radio, right? So radio waves is another example. Earthquake, it's another wave. So it's a vibration on the earth, right? On the plate tectonics on earth. So it's vibration. And traffic waves. Maybe you're not quite familiar with traffic waves because you don't watch it from the eagle eye. When you're traveling on a traffic, you don't really care whether it is a wave or not. But if you go to a eagle eye view, like from a helicopter or something, if you're looking from high in the sky, then you will see like the cars are moving in a pattern. So they're going closer to each other. Then there's a distance between the cars. Then they will be closing to each other. Then there's a distance, right? So it's a wave. Then light waves is another example of waves. These waves, everything are waves. It's happened due to the vibration in time, in space. But the way that it's propagating energy and the way that it vibrates the molecules, or does it need a medium to propagate energy? So those things will be varied. So to explain the waves, we need to know a bunch of things, right? So basically, we know that sound waves need a medium to propagate, and light does not need a medium to propagate. So example, the sound waves. So if we put ourselves inside a vacuum space, vacuum means you remove all the air molecules in the room. And if we start talking, other people can't hear us. So what do you think about astronomers? So if there are a couple of astronomers in the space and they're trying to talk to each other, can they really hear each other? You know, like in space, in many places, there's no medium. It's empty, right? So I say many places because when we enter into a planet, there are some planets having atmosphere. So if you think about just in space, like there's no medium inside, so it's a vacuum space. So when astronomers talking to each other, they can't hear each other. So they are using sign language, or they talk to the equipment, and the equipment is propagating the energy somehow, and it's converted into electromagnetic wave, right? So if we go to the space and if we try to talk to each other, we can't do it. We can't hear each other. We can talk, but we can't hear each other. So sound need a medium to propagate. But light, like we receiving light from the sun to earth, right? So on the way, there are empty places. It's vacuum space, right? But we still can receive the light. So light does not need a medium to propagate. Isn't that interesting? So there should be two different type of waves, right? So we will talk about light in the next class. It's a big topic because light is a vibration of electric field and magnetic field. So I believe you are familiar with electric fields and magnetic fields somehow by now. So light is just a propagation or a vibration of electric field and a magnetic field. But sound, it is not. It is just vibrating any medium around it. So we can propagate sound in the water or in air. All right. So when we characterizing the waves, we need to know several parameters like amplitude, wavelength, period or frequency, and also the velocity or the speed. Velocity means directed speed. So if you're talking about something moving, we can always add the direction. So are we moving to the left or are we moving to the right? So likewise, you can add a direction to the speed. So we call that as a velocity. So when we talk about motions in the future, we'll learn these topics like velocity. What is velocity is. But for now, remember that velocity is a directed speed. That means there's a speed. At the same time, we need to mention the direction of that speed. Right, so amplitude, wavelength, period or frequency, and the velocity. So those are the parameters that we need to mention when we are describing a wave. All right, so here, that's a typical wave. We call this as a sine curve. What is a sine curve? So in mathematics, you know, SOHCAHTOA, right? So in there you have sine, cosine, and tangent. So if you plot the sine values in terms of changing angle, you will see a variation, which is a shape of this. So we call this as a wave shape. Also, we call this as a sine wave. It is like S, right? So S wave or a sine wave. So if you look at this one, here we have a peak value, right? So the high value, and here we have a like a trough. So it's a valley, right? So peak and a valley here. So wavelength means the distance between successive like positions on a wave. So likely points. So a peak to peak distance. Okay, so if you draw a line like that, you see this is the amplitude. I'll talk about amplitude in a minute. But if you look at this peak over here, and oh, my animations are not aligning well. All right, so here's a peak and here's another peak. So the distance between peak to peak is the wavelength. At the same time, you may measure the distance between this valley to this valley. That will be the same value as this one in a perfect world. If there's no damping, like nothing to stop it, if there's no resistance to propagate the waves, then the valley to valley distance and the peak to peak distance will be the same. Anyway, so the definition of wavelength is the distance between successive like points on a wave. So example, peak to peak value, distance from here to here. Okay? So the wavelength symbol is this letter lambda. Look at this. It's like a, what is it? It's like a curved line over here and a straight line over here, right? So this is the lambda. So lambda is a Greek letter we are using to represent the wavelength. So we, you know, like in physics, we are using symbols and also we need units to explain some quantity, right? So lambda stands for the wavelength. And the units to measure lambda. It is a distance, right? So we can use meters, nanometers, millimeters, right? So we can use any unit that used to measure distances to measure the wavelength. Anyway, the symbol for wavelength is lambda in physics and chemistry or even in biology. Right? So here, again, this distance from valley to valley, the bottom points, that's the wavelength. So you need to pick the minimum value here and the minimum amplitude here, and then you measure the distance from here to here. That's the wavelength, and its symbol is lambda again. And the amplitude means the high of the wave. So if you draw a center line, you are dividing the wave into two equal parts. And if you measure the height from the center line to the peak, that is amplitude. You can even measure the the distance from the center line to the valley up here, down here, right? So down here, that's the amplitude again. So in an identical situation, I mean, ideal, sorry, not identical, it's ideal situation. In ideal situation where there's no air resistance or nothing to disturb the wave, then the amplitude will stay the same throughout the time. All right, so this is a illustration of changing the wavelength and or the amplitude. So as you see here, the top wave is the original wave. So we are going to compare the other waves with this one. Here's the original wave. So you just eyeball the values, the wavelength and the amplitude of the wave. So then look at the second wave here. So here we have a shorter wavelength, and all right, so hold on. Okay, so here's the center line to the wave. So it's dividing into the wave into the two parts here. So look at the amplitude. Here, the amplitude of the original wave, let's compare the other waves with the original one. So it looks like it has the same amplitude here, but here it is kind of a chopped, so it's smaller amplitude, it's short, right? And this one also a shorter amplitude, that means small amplitude, it's small in height. And then if you draw like connecting the same points on the each wave here, you can compare the wavelength. Now here, from peak to peak distance, that's the wavelength of the original wave. Now here, the peak to peak value is less than the original one. So this have a shorter wavelength, right? The peak to peak value here, the distance from here to here is shorter than the original one. So it is a shorter wavelength. This one, peak to peak, is about the same as the original wave. So it does have same wavelength as the original one. And here again, it has a shorter wavelength because peak to peak distance is shorter than compared to the original wave. So in this one, we have shorter wavelength and a smaller amplitude compared to the original one. This one has the same wavelength but small amplitude. Here, shorter wavelength but same amplitude. Okay. So when you're comparing the amplitude, you need to draw that horizontal line like this one. And when you're comparing the wavelength, you need to draw the vertical lines that's comparing the wavelength of the waves compared to the original wave. All right, so the next parameter is frequency. So frequency, we are using the symbol F, the letter F, that is the symbol. Then the units is per second. So S to the power minus 1. Minus 1 means per second. And it is equal to hertz. It's uppercase H and lowercase c, hertz. That's the frequency of a wave. So maybe you have noticed this symbol in any electrical equipment. So if you look at your, let's say, that's my power cable for the laptop. So you may do the same. So you can take your power cable of your laptop, and if you check the values that's given on the battery here, not the battery, the power adapter, so you can read the values there. So there's some, without glasses I can't read, so let me wear it and see whether it is. Still I can see it. Okay, it's dark here, so I can't read it, but you should be able to read some hertz value here. So that's indicate the frequency of the incoming the current wave or the voltage wave, right? So it should be 50 or 60 hertz in a power adapter in your computer, right? So you may check that. It does have this symbol Hz. That's the hertz. That's the frequency of the motion of that current wave or the amplitude of, sorry, the voltage wave. All right, so basically frequency is the number of waves which passes a given point in 1 second. So you measure 1 second and see like how many number of waves can it pass through. Number of waves, how can we measure number of waves, right? So one wave means peak to peak. So if you count waves that you're counting from peak to peak. So when you're passing one peak and when it's past the second peak, that's one wave. And so likewise, you can count number of waves that passing through a particular point in 1 second. So that will give the frequency. All right. So the frequency, as I mentioned, the symbol is F, and that means number of vibrations per time. So if you put it into the equation, it's 1 vibration divided by 1 second. So there's no units for vibration. So you're basically dividing a number by 1 second. So the unit is hertz. So per second is hertz. So 1 vibration per 1 second, that will be 1 hertz. So if there are 50 vibrations per second, then the frequency is 50 hertz. If there are 200 vibrations per second, then it's 200 hertz. All right, so the high frequency waves, look at this one. Actually, if you're a music person, you can demonstrate that. I do have my guitar here, but it has broken strings, so I cannot really demonstrate it. No. Here, low sound, high sound, bass sound, right? So it's, honestly, I cannot demonstrate it using this one because it has broken strings. Anyway, so high frequency and low frequency. So look at the graph here. So high frequency means there are whole like higher number of waves fitted into a one place, right? So let's say this is a period. So this is a one period here, and here's a period for this one. So it has, the period is longer over here than this one. So if you measure the period for a one particular wave, then in a low frequency, it's take longer time to pass through, right? So here we can fit a lot of number of waves into particular time frame. Here we have only few number of waves here. So this has a low frequency wave. So high pitch, we call this as a high pitch, and this will be a low pitch. Okay. So if you're a music person, I believe your ear is tuned to high pitch and low pitch. So you should be able to recognize which one is high pitch or low pitch. So high pitch means you have a high number of waves fitted into a short period. And in the same amount of time period, we have only few number of waves fitted in. So that's a low frequency wave. So this Hertz is named after the German physicist Heinrich Hertz, who lived in this time, 1857 to 1894. So he's the first person to provide conclusive proof of the existence of electromagnetic waves. So electromagnetic waves is our top communication medium, right? So your phone. So here I have a phone and you have a phone. If you dial my phone number, then I can quickly receive that phone call, right? So that's happened from the electromagnetic waves. So for your phone number, it has its own pattern of electromagnetic waves. So when someone dialing that number, you're going to resonate with that dial tone, so the dial number, and you can hear it. So it's a high technology, but the basic idea is electromagnetic wave propagation. So electromagnetic wave is propagate to your phone from your friend's phone when he's dialing you, and then the phone is catching that electromagnetic wave. We'll talk about electromagnetic waves maybe today or on Thursday. All right, so he's the first person to come up with the idea about electromagnetic waves, and that's developed the technology a lot in the communication wise. All right, so the velocity of the waves. Now, like some waves are traveling really fast. So if you observe a water wave, like if you drop a stone to water, the shallow water, then you will see it's producing waves, right? And that wave is propagating with the speed. You see, like it's moving with the speed, right? So velocity is a really important factor when you're describing a wave. Again, velocity means directed speed. So there's a direction to the wave. All right, so any wave, like for example, light or sound, it does have their own velocity value, right? So I think I do have numbers. Okay, look at this. These are the wave speed for particular waves. So for light, it's 300,000 kilometers per second. For sound, it's 340 meters per second. Earthquakes is 2 to 4 kilometers per second, and tsunami waves, it's 600 to 800 kilometers per hour. I should have the same unit here, right? Kilometers per hour, kilometers per second. So sorry about that. I should have included a same unit here. Anyway, you can compare this value, light and sound. So sound is much slower than the light, right? So 300,000 kilometers, here 340 meters per second. So within a second, sound can travel 340 meters. Here within a second, light can travel 300,000 kilometers, right? So there's a big difference here, right? So the light is faster than sound. That makes sense. That's why when it's lightning and thundering, we hear the sound, the light, we see the light first, then we hear the sound, right? So that's because of the speed difference. All right, so to calculate the velocity, we can use the frequency of the wave and the wavelength. So when you take the frequency and multiply it by the wavelength, you can calculate the speed of the wave. So here we represent the velocity, wave velocity, and the F is the frequency of the wave that we measured in hertz, and lambda is the wavelength. Again, the velocity means the speed, right? So speed basically distance divided by time. So if you are traveling by a car, and if we say like I'm traveling with 60 miles per hour, so you're talking about like how many miles you are traveling in 1 hour, right? So that is the speed. So similarly, you can calculate the velocity by taking distance divided by time. However, we can also calculate the speed of these waves by using this equation, which is F times lambda, F being the frequency and lambda being the wavelength. Now, lambda, as I mentioned, you can measure the wavelength in any unit that we are using to measure distances. So you can use meters, kilometers. When we go to the really tiny waves, we use nanometers or micrometers, right? So likewise, but when you have different units here, the units for velocity will change. So if you use meters here, it will be meters per second. If you use nanometers, it will be nanometers per second. So likewise, depending on the wavelength unit, the velocity units will vary. Now here, 300,000 kilometers per second. So the unit to measure wavelength is kilometers here in this value per second. So again, each wave has their own velocity values. All right, so there are two types of waves. One is transverse wave, the other one is longitudinal waves. Yeah, I wish we can do demonstrations in the class. Anyway, I'll show you some simulator, then we can use that to understand a little better. But anyway, before I take you to the simulator, let's look at this slide first, and then I'll take you to the simulator and let's play around there. All right, so have you ever played with a slinky? Even when you were a kid? It depends on which generation you are. So you are in a younger generation, so maybe you are not, but also if you're a person that who play with a lot of toys, maybe you have played with slinkies. Slinky is a kind of a solenoid, like it's a wrapped mechanical piece. Okay, so this is a picture of a slinky that vibrates, like we hold it from this end and then vibrate like horizontally like this, right? Hold on, not horizontally, the vertically. So you're vibrating the slinky vertically, then you will see a wave that's create like this one. It's like in the top picture here, the first picture here. Why my cursor is doing crazy here? I don't know. So please look at the first picture on this slide, which is picture A. So as you see there, the slinky is moving up and down, but there's a wave that propagates in horizontal direction. So these are called transverse waves. The oscillations that is perpendicular to the direction of wave travel. So wave travels in horizontally, but the molecules are vibrating up and down vertically to the wave propagation. Now, the second picture, the picture B, that shows a longitudinal wave. So you take a slinky and you vibrate horizontally, like parallel to the ground. Then you will see in some places it's come closer, like the stretch and compress, stretch and compress. So that is a longitudinal wave. Okay, I know you don't get it. So let's go to a simulator and watch it from there. So sound waves are longitudinal wave. So when we speak, the air molecules get vibrates, like it's stretch, compress, stretch, compress. So likewise, it propagates in the air, right? So sound waves is a longitudinal wave. Now the electromagnetic waves are transverse. So basically light wave is a transverse wave. All right. So let me take you to the simulator. Okay, give me a second here. All right, so on this one, you see a string. This is a string here, and I can give some pulses here. So let's say I'm giving a manually, okay? So I'm trying, I'm holding the string from this side, let's say. So here, it's pretend our arm, let's say. So from there, I can vibrate it. And here it's has a fixed end. So I have a clamp here. So it's a fixed end over here. And I'm going to send a wave by vibrating it vertically. So I'm going to vibrate it vertically up and down. So here, just one symbol, so it's a wave, right? So when the wave propagate all the way to the end, it's reflect back, right? And it's keep happening. All right, so let's oscillate. We start. I'm going to oscillate this. So I'm making like it's vibrates. All right, so let me start again. Pause. Please start. Right. So observe it. In the beginning, there will be, I will put it in the slow motion. So in the beginning, when it oscillates, there will be a wave that propagates, and at the end, it will reflect back. In couple of seconds later, you will see that the initial wave and the reflected wave will combine, and it will create like a nice resonated wave here. All right. So observe that. Okay. So it's sending a wave and it's get propagated. And at the end, it will return back. Now it's come to a resonant. And look at that. It's making the maximum possible amplitude here for this particular wave. Right? And it's go back. So it's keep vibrating, and it's resonate, and it's lose its energy. It vibrates back and forth. Now, the main idea here for you to look at is the particles here. So this is the string, but you see the particles over here? There's a wave propagate horizontally, but the particles move up and down. Do you see that? The wave, you see a wave propagates, right? Horizontally and come back. So there's a wave going on horizontally, but the molecules in the up and down. Okay. So that is a transverse wave. Wave propagation is perpendicular to the molecule movement. See these molecules or the particles, they're moving up and down, but the wave, we see that it propagates horizontally, left or right. Okay. All right, so let's send a pulse. So I'm sending a pulse here. It's just the same, right? So it's reflect back and it will keep moving, but you see a wave propagates horizontally, right and to the left, but the particles are moving just up and down. They stay the same at the same location. See, like if you observe this point over here, it went up, it came down. It went up, it came down, but it did not move horizontally. That's what I mean. So transverse waves, the particles in the object are moving up and down, but the wave propagation is horizontal. So they're perpendicular to each other, right? Horizontal and vertical, they're perpendicular to each other. So we say that in transverse waves, the molecules vibrate in perpendicular direction to the wave propagation. All right, now let's look at the water waves. I can even put the sound, because we talked about sound. So In air, we see a lot of air molecules are here. It could be oxygen, carbon dioxide, nitrogen, or anything, right? So we have what is the percentage of oxygen we have in the air? 80%? 10%? Yeah, we have about 20% oxygen, roughly, and about 78% nitrogen, right? So even though we need oxygen for our breath, we are breathing the whole bunch of air, like 78% nitrogen and 20% oxygen, and a tiny percentages of carbon dioxide and other air. So anyway, so air molecules are there. So here these dots represent the air molecule. It can be anything like nitrogen, carbon dioxide, oxygen, whatever, right? So these are the air molecules that represents here. And these red dots, just for our reference, like to see like how it vibrates. Now here's a speaker, so I can create a sound wave, and let's see what these air molecules are doing. So there's no wave propagating here. Now I'm going to send a wave. So a pulse. Okay, it's already propagated. I don't know whether you notice it or not. So let me send it slowly. See, now the wave is propagating here. So all the molecules are vibrating, and the wave propagation also in the same direction as the wave vibration. All right, so it's hard to see. So let's send a wave, like a continuous wave. Do you see that the air molecules are compress and stretch, compress and stretch? And I see that the wave is propagating in horizontal direction. And let's observe one of these red dots. So this red dot, it's compress, stretch out, compress and stretch out. So the molecule vibration is in horizontal direction, and the wave propagation also in horizontal direction. So the particle movement is in the same direction as the wave. So it is a longitudinal wave. Yeah, so if you look at the wave type, then you will see it kind of like this. So you see that this is the compressed part, stretch part, and compressed part and the stretch part. So it's propagating in horizontal direction. Here's a particle. Let's put both particles and waves, so then you can see it clearly. See, the particles are not going away. They're just vibrating here and there in the same location, but they compress and stretch here. So they're going to compress region and then jump back to the stretch region. So likewise, it's why wave is propagating. Okay, so let's try play tone so we can understand. It's really annoying. Okay. Yeah, so let's look at it in a graph. In a graph, you see it like, okay, so here's the place that it's created the wave, and it propagates along the horizontal way. So this is the position and the pressure here. So it's propagate here, and it's air molecule, so it's kind of damping out from this region. But later on, like when we go all the way to the space, it's get damp out and it lose its energy by vibrating to each molecule, each other. So it's 10:15. So let's continue a little bit on the PowerPoint slide. Then I'll take you to the top pattern. Let's do a couple of questions and the attendance. Okay. So here's another picture comparing the transverse wave and longitudinal wave. So in a transverse wave, the molecules are moving up and down, and the wave propagation is in horizontal direction. So they're perpendicular to each other. Longitudinal waves, the wave propagates horizontally in this picture, and the molecule movement, it's compress and stretch, it's happened horizontally as well. So they are in the same direction. Okay, so you notice that the wave is not taking matter. It's not taking the air molecules away. Air molecules are still here. When I speak, air molecules over here stays the same, but when I speak, it's just vibrate, right? So it does not carry the matter, but it does carry something else, right? Because otherwise, how can it get distributed or propagated. All right. So for an example, let's think about a whip. So when you have a whip, I wish I could use a whip here. So you know, like when you use a whip, you just move it vertically. And do you see that the whip is moving? So when I hold a whip by my hand, it will stay there, right? But when I move it, its particles are moving up and down, but the whip is not going to go away from my hand. So the whip is not moving. Do you like to stay in the end of the whip? If you know what is a whip is, you will not. It will hurt, right? So you don't like to be at the end of the whip. Why? So if the wave is not taking any matter, then why should we worry about standing up at the end of the wave? So there's something coming in, right? So it will hurt us. So there's energy that's propagated through the wave. So even though materials are not moving, it's just vibrate here, the wave is taking the energy. So light wave is emitting from the sun and it's come to our planet and it brings energy. So energy is coming as an energy packet. It has their own energy packs there and it's reaching over here onto the earth. So we'll talk about dual nature of light in the next class or the following class. So where we can learn about like how the light brings energy on their wave. Okay? So now we are ready to define the wave in a better way. So we can say a wave is a traveling disturbance that transmits energy with not net movement of matter. Remember, it's no net movement. Net means a total movement of matter. Then the disturbance is frequently called an oscillation or vibration. The substance through which the wave travel is called the medium. So when we are talking about sound waves, and if I am speaking within the air, then the medium that I'm using to propagate the sound wave is air. So likewise, this is the correct definition or a full definition of wave. So wave is a traveling disturbance that transmits energy, not net movement of matter, and the substance that we are using to take the wave propagate is called the medium. All right, so the amount of energy that transmit by a wave is proportional. So I believe you know the word proportional now. When you increase something, the other thing increases. If you decreases the one thing and then the other thing decreases. So they're proportional. They're changing according to the next one in the same fashion. So the amount of energy that transmitted by a wave is proportional to the square of its amplitude. So we know amplitude is, so you know, like the height of the wave. So if we know the amplitude, we can calculate the energy. So I'm not going to go in detail about what is this constant is. It is a constant. So it doesn't matter where you are or what you're using. It is a constant value. So energy of a wave is equal to a constant times amplitude to the power 2. So A represents the amplitude. So amplitude to the power 2. Okay, so that is the energy. Now let's try this one. So assume, don't look at the answer. I already have the answer in there, but here's the problem. So assume that a wave with the amplitude 5 meters hits a coast. So let's think about a tsunami wave. So the amplitude of the tsunami wave is 5 meters and it hits the coast, followed by a wave with the amplitude of 10 meters. Maybe you were little at that time. So in 2004, in East Coast, we had tsunami that's happened by in the area of Indonesia, and the waves came like all the way to South India and Sri Lanka, and in the whole area. So Indonesia, that Indonesian islands. So we had a huge effect from tsunami waves. So when the tsunami comes, suddenly the coast got like all the water in the ocean went all the way back to the ocean, and suddenly it came back to the earth, the ground with a amplitude wave, high amplitude wave, and then suddenly it went back and the second wave came in with the double size of a wave size. So that's damaged a lot. Like it's took over a huge train off from the track, and it's took a lot of I think you are familiar with those tsunamis, right? So you may watch those videos. It's amazing that the water has that huge energy to take over anything, that any big size, like heavy weight objects. So anyway, so go back to the question. So initially there's a wave with the amplitude of 5 meter, and the second one with the amplitude of 10 meter. So it's asking how much more energy will the second wave deliver. So you're basically trying to compare the energies in two waves. So in the first wave, the amplitude is 5 meters. Right, so we know that the equation for waves goes with the amplitude to the power 2. So energy goes with the a to the power 2. Here a means the amplitude. You should take notes because I didn't include that a is the amplitude here. It's on the above PowerPoint slide. But remember that the energy of a wave proportional to the amplitude to the power 2. So we know that the energy is equal to a constant times the amplitude to the power 2. Now let's look at the first wave. So I use 1 to represent the first wave. So energy of the first wave is equal to a constant. All right, we are not bothering about what is that constant is. Constant times, sorry, I'm using an asterisk mark here, but it should be multiplication, right? So multiply by amplitude to the power 2. So here 5 to the power 2, it's 5 times 5, it's 25, right? And let's look at the second wave. So second wave, which is energy of the second wave, is equal to a constant times the amplitude to the power 2. So here amplitude is 10 meters. So 10 to the power 10, which is 100, right? So now if you divide E1 by E2 or the E2 by E1, I need to compare the second wave to the first one. So I take E2 divided by E1. So I get 100 divided by 25 over here. So if you divide 100 by 25, it's 4. Okay. So you need to know, you should know how to do this calculation. So this is comparison of energy. So E1 is constant times 25, E2 is a constant times 100. You take E2 and divide by E1. So when you divide E2 by E1, you get constant times 100 divided by constant times 25. Constant is the same, so it's cancelled out. So you end up having 100 divided by 24. That will be 4. So the first wave, second wave is 4 times energetical than the first wave. So it's delivered 4 times higher energy than the first one. All right. So depending on the wavelength of frequency, it's have different effects on us and on the environment. So examples are audible frequency range. Audible means the range that we can hear. Hearable range of frequency of waves is 20 hertz to 20,000 hertz. It is a very small range in the frequency curve because it can go from 0 to a huge frequency, right? So we can hear only 20 hertz to 20,000 hertz. So if you have a dog and if you're using a dog whistle, then we can't hear the whistle, but dogs can, right? So it's really researching them, the dogs. So that has a different audible region for dogs. So the dog whistle is go from 23 to 54 kilohertz. Kilo means 1,000 times, okay? So here we have 20 hertz and 20 kilohertz. Here it's 23 to 54 kilohertz. So it's beyond the human's audible range. So that's why we can't hear the dog whistles. Then the dolphins produce sounds with a frequency of up to 150,000 hertz for echolocation purposes. So, you know, like they're using echolocations. So they're using this high frequency values. See, this is the frequency curve. So these are the sound frequencies go from 0 to 800,000 or 80,000 in this graph. And humans can hear only very small region of this the sound frequencies. All right, so look at this graph. So here, the elephants and moles, they can hear less frequencies than us. So they can hear from a little bit, not 0 exactly, but 0 means there's no wave, right? So anyone can't hear it. So something in between 0 and 20, or little beyond 20, they can hear, elephants and moles. But humans, we are in 20 to 20,000 hertz. Dogs and cats, they can hear the frequencies that we can hear. So there's a little overlap here. So they can hear somewhere here, like. All right. So the cats and dogs, they can hear a little beyond than us, so up to 40,000, right? So dolphins and bats, they can hear further away. So because they're using echolocation, so if they want to navigate, they're sending a sound wave, and then they propagate with that. So from the Doppler effect, we'll talk about Doppler effect as well. All right, so it's 10:25. So I think I should take your attendance and do a couple of questions in there. Okay, please send your attendance code. Okay, so whenever you get, most of you, when you're unmuted, I see a lot of noises and a lot of communications going on. I really want you to engage with me. I know it might be really hurting to listen to me, but you can always question yourself and you can stop me and ask questions. It's okay. So our goal is not to be a greatest scientist in the world, but we can learn a little bit science, right? So please be with me. You can do other things later. I need only 1 hour and 15 minutes from you. You have 24 hours, so you have another 22.5 hours that you can do anything else. All right, so please send me your attendance code.
Hi, I have a question.
Yes.
What is our exam based on that's on the 6th? Is it just based off of the last homework we did, or are we going to get another homework assignment that's going to be based off of it as well?
All right, so we in the first exam, like, covered the electricity, right? So anything after that until last week, Thursday. So it's
okay.
magnets, magnetism, and magnetic induction.
That's what I figured. Okay, thank you.
Homework. I had only one homework, and then also you have questions on top hat. You can try those.
Okay.
And study the materials. And it's open book.
Okay.
You can
use thank you.
Notes. All right, so here's the first question for today. I still have the attendance code open, so please try sending it.
I have a question.
Mm-hmm.
So for the last exam, we had the questions on Top Hat to review, but there was also an exam tab that had the questions in one spot. Could you do that for this exam?
Okay, so for this exam, I'm not going to put any practice exams because it will be identical then, because you have access to everything. Like you can access to Top Hat, or you can access to the homework or anything while you're taking the exam. So I'm not going to send you the any more questions because homework should be helpful. Most of the time, my exams are mainly based on homeworks and the class material. So please try the questions that we did in the class and the homework. That would be enough. Because I'm not going beyond those topics in the exams. I don't need to test you from something else. Okay, so I'm not going to open any practice exams. It does not make sense because if I do, I will have the same question in the exam. Yeah, you can, okay, I will give you some clues. Like you can go to the homework and try the problem, like, like when we bringing a North Pole towards. Now you may imagine like what happened if I take North Pole away. So you have to reorganize the problem and just analyze it. I'll show you a couple of questions later. So what time is it? 10:30. So yeah, we do have time. So give me a second. Let me finish these couple of questions and then I'll take over you with the homework. Then I'll go over a couple of questions. All right, so I'm going to stop counting the attendance. I think all of you are good because I kept it open for a while now. Okay, so the first question, it's asking a wave disturbance in which the displacement in the medium is parallel to the direction of travel of the wave. It is a transverse wave or a longitudinal wave? Look at your responses. Yeah, it is a longitudinal wave. If the wave is propagating in the same direction as the medium propagates or the vibrates, then it is a longitudinal wave. Example is a sound wave or a waves on water. Okay, now it's asking what if the medium is perpendicular to the direction of wave travel or the wave propagation, is it a transverse wave or a longitudinal wave?
Hello,
Yes.
I have a question.
Mhm.
Beach waves are transverse waves or longitude waves?
What do you, okay, so what is your question? Can you ask it again?
Beach waves, are they transverse waves or longitude waves?
Are you asking about this question
No, no,
or
no.
overall?
No. A question for me. Like, it's not about the top
Okay,
half.
so let me finish this question and then I will go over then because that is the one I was talking from morning. So let me finish this one, then I'll show you the slide again. Okay,
Okay.
so let's look at this. Okay, yes. So if there's a wave that the medium vibrates in perpendicular to the direction of travel of the wave, then it is a transverse wave. So I think Lisbeth talked to me earlier, right? So maybe you have this, everybody have the same problem then. Let's go see again. So
It wasn't
two
me.
types of waves. We have two types of waves. One is transverse wave and a longitudinal wave. So in a transverse wave, particles are moving up and down, but the wave propagates perpendicular to that. Then the longitudinal waves, it stretch and compress, stretch and compress. So the wave propagates in the same direction as the particles stretch, compressed. So that is a longitudinal wave. So sound wave is a longitudinal wave. Transverse waves, examples are light. So light wave is a transverse wave.
I think she was asking what type of beach waves.
Oh, beach. Okay, I heard beach.
Yeah, I said beach.
Oh, sorry. I thought you didn't get the idea here. Okay, I'm sorry. Beach wave. So you are talking about the ocean waves, right?
Yeah,
So
yeah.
ocean waves, it has both. You know, like the particles are moving with the wave horizontally and also moving up and, no, hold on, it's water wave, right? So it should be longitudinal waves because the particles are moving in the same direction as the wave propagation. I don't know, I have to search because I think it comes with both, because sometimes we see like it's just moving up and down in a shallow water. In a shallow water, the water just go up and down, but you see a wave propagation in horizontally. So it is a transverse wave in sometimes, but when you see like waves is propagating like in oceans, wave fronts, like it's coming towards you, right? So it's a longitudinal wave. So yeah, beach waves, it depends on the condition. So sometimes it's a transverse wave, sometimes it's.
Okay, thank you.
But sound waves are, it's not changing, it's solid. I'm sorry, Lisbeth, I thought you were talking about like which waves are transverse. So that's why I took you back. Okay, let's look at your answers. Yeah, I think about 20 of you didn't get the idea yet. So please read the slides and maybe listen to me again. Also, I thought maybe you can use the PBS Crash Course Physics if you like to watch something like visual aids. So PBS Crash Course is a recommended video series that you can use if you like to. And remember, like I'm not taking in the exams, I'm not taking you beyond what we have talked in the class. So when you're using other resources like videos available online, make sure you're not confusing yourself. But if you have questions, you can always talk to me. Okay, so answer should be longitudinal waves. Sound waves are longitudinal. All right. So this is a calculation. So I want you to try that. So we have a wave amplitude of 5 meters that hits the coast. And then it's asking a second wave with 100-meter amplitude. So how much more energy will the second wave deliver? Okay. So the equation, if you remember, energy is equal to constant times a amplitude to the power 2. Can you still see the question? Because on my screen,
Yes, we can.
Yes.
all right, so if you didn't hear me properly, for the next exam, we don't need the lockdown browser. It is an open book. So you may look at the syllabus and look at the schedules. There I listed down like second exam is open book, open resource test. And it does not need, we don't need lockdown browser, right? So don't worry about having lockdown browser, but rest of the exam, you need to have lockdown browser unless there are any problems. So I sent an email asking about for those who does not have a VCU ID. I am still waiting for the reply. Once I receive the reply, I'll let you know. So if you don't have your ID, let me know before the third exam. So you have to be on the Zoom meetings while taking the exam. Okay? And those who missed the first exam, you need to reach to me with a make-up date. I know like there are a couple of students who didn't reach to me yet. All right, so I will.
Hello? Hello?
Yes.
I just want, you said for the next exam, whenever we have that next exam, we don't need the lockdown browser. We just need, it's an open book. But the one after that, we need the lockdown browser?
Yes.
Okay. I just want to make sure because I need to get the
After
lockdown
that,
browser on my
and
computer.
also for the final exam, for sure, it is a VCU rule that final exam should be using lockdown browsers.
We don't need our student IDs until the final exams, right?
Yeah, that's why I'm trying to get somehow make those IDs mailed to you or find another different way that I can check your V number or something, checking in. So I'm still on that process. So anyway, for this exam, this upcoming exam, we don't need to worry. So
Okay, thank you.
all right. So what is the answer for the first question? I lost my top hat. Yeah. Okay, where is it? Here you go. But do I sharing top hat or not?
No.
What is? Okay. It's gone from my screen. Oh my God. That's my top hat. I can't share it anymore. All right, let's see. That's weird. Okay. I have it here. Then share screen. Here you go. Okay, anyway, so these are the answers I got. Can you see the answers here? So the correct answer is B. Okay, so let's try that because only 50% of you got it correctly. So let's work on it. So first wave is, the amplitude is 5 meters. Second wave amplitude is 100 meters. All right, so let's try it here. So we know that the equation for energy is E for the first wave is a constant times the amplitude to the power 2. So it's 5 to the power 2, right? So it will be 25. I believe you got it. And for the second wave, it's E2, the energy for the second wave, that's equal to a same constant times amplitude to the power 2. So it's 100 times 100, right? So it will be 0, 100 times another 100. That's how it is, right? So basically E2 is equal to a constant times 1, 0, 0, 0, right? All right, now we have to compare. So we take E2 and divide it by E1. So I get E2 divided by E1. So that will equal to what? I'm just making my division. So this is equal to, I get a constant times 25 divided by a constant, the same constant times 100,000.
Wouldn't they be switched though?
Yes, because E2 divided by E1, right? So this is 25 and that should be 100. So that's my eraser. Right, so here it will be constant times 100,000. All right, so you do that. So this constant will cancel with this one, it's a divide, right? And you get only 100 divided by 25. 100,000 divided by 25. So answer will be 400. Yeah, so I agree. I didn't see who speak to me earlier, so thanks. So it should be E2 divided by E1. So it should be constant times 100,000 divided by constant times 25. So here this constant is the same, so you don't need to worry about that. Only thing you have to find the ratio between the amplitude to the power 2's. So it's 100,000 divided by 25. Those who answered 4, I think you just followed my previous question where I had the amplitude to be 10. So that's what I mean, like in the exams, you will see same type of question, but there's a little change there. So you need to be alert. So please read it carefully. So it will be easy for you.